Hello WHS Juniors. Today is another instructional vignette, actually the fifth one we've done here in our little series in preparation for your wonderful MCA test. There's a blizzard warning going on right now, but I look outside, looks like it's almost going to clear up, so looks like the weather guys maybe made another mistake. Hopefully I won't make too many today in our video on exponents. So this is going to cover just about everything you could possibly see with an exponent. Don't know if you'll see a lot of these problems on the MCA part of the test, but certainly on the grad part you've got to be able to work with exponents in expressions. So here we go. If you remember, every exponent has a base, and the base is what's involved in the repeated multiplication. So I'm going to go through different power rules here. If you're multiplying common bases, basically the power tells you how many of that base you have. This means 2x is multiplied, this means 3 multiplied, and rather than writing it all down, we simply add the exponents. So it'll be x to the 5th power. Okay? Quite simple. If you have an expression for a base that already has power and it's raised to an outside power, essentially you have groups of factors. This is x squared cubed, so you would have x squared times x squared times x squared, and rather than write that all down, essentially you're grouping factors. So 2x's, 2x's, and 2x's make 6 of them. So essentially, when you have powers, what I call stacked, a base with a power to an outside power, you can simply multiply those powers. So that'll be x to the 6th. All right, going to our next expression. I've got a whole bunch of stuff in parentheses. And parentheses are used as a grouping symbol here. All of these items need to be raised to the outside power. So it's negative 2a cubed b squared cubed. I start with the sign actually. Negative to the 3rd power, that would be 3 negatives multiplied together. If you remember, when you're multiplying with negatives, an odd number of negative factors makes a negative product. So it's going to be negative. And then I got to raise 2. One of the things I think is really important to avoid mistakes with exponents is to say the word times as you're taking and working with the base. This means 2 times 2 times 2. A common mistake is just to multiply the base with the power and say it's 6. That would work if it was repeated addition, but it's repeated multiplication. 2 times 2 times 2 is in fact 8, and there we go. Then we've got a couple of letters with power stacked to outside power, so we're going to multiply those exponents. So a to the 9th, b to the 2nd to the 3rd, multiplied b to the 6th. Okay? Now the 4th example here, I've got h to the 6th in the numerator and h to the 2nd in the denominator. Remember, when you multiply common bases, you add the exponents. Here we got actually a battle going on. The h's up top are all multiplying. But if you have a variable in the denominator of a fraction, it's really repeated division down there. So what happens here, we could write this all out. I've got 6 h's up top, and I've got 2 h's on the bottom. And in fact, these 2 h's are dividing, and they would undo or reduce 2 of these h factors, leaving you an extra 4 h factors in the numerator. So teachers teach just subtract the powers. I say just look at the powers. If you have a base on the top and a base on the bottom, it's a battle. It's a battle between multiplication and division. And I simply teach my kids who's going to win that battle and by how many factors. So there's an extra 4 factors up top. This would be h to the 4th. And sorry about that. There's an extra 4 factors up top. If we go to the next problem, I don't have to teach subtract on this. I just simply look at it and say, hey, there's c's on the top that are multiplying, there's c's on the bottom that are dividing. It's a power struggle. There's an extra 2 c's down here, so it's going to be 1 over c squared, which would be the same as c to the negative 2 power. Okay? All right. If you remember, a base with no power, a powerless base, is actually the number 1. 1 is the only number that doesn't matter when you multiply or divide. So a powerless base is truly just 1. Now when is 1 important and when is 1 not important? Well, if you look at the next expression, the base for the 0 power is just x. So it's x to the 0 is 1, 2 is multiplying that. Since 1 doesn't matter when you're multiplying, the answer here will just be 2. So essentially you could have erased that x to the 0 part of that expression. The next one is 2 plus x to the 0. Now you're combining this base to the power 0. 1 matters when we add. 2 plus 1 is 3. Okay? So if you see a base of 0 or a power of 0, that base to the 0 power is equal to 1. Alright, moving on. Positive power means repeated multiplication. Negative power, in fact, means repeated division. Now if you remember what I just said, division occurs on the top or the bottom of a fraction. It occurs on the bottom. So one of the things that we teach kids is if you have a base to a negative power, we say it's the same as the reciprocal to the opposite power. So the reciprocal of 2 would be 1/2, and the power would turn to 3. Now what I prefer to say to kids is, hey, if a negative power means division, we should put that base in its place, which is in the bottom of the fraction line. So if you have a negative exponent on a base, all you have to do is move that base across the fraction line, and the power will turn to its opposite. This literally means divide by 2 3 times, and you can see that's exactly what we have here. So when you have a negative exponent on a base, you need to move that base across the fraction line, and the power will turn to its opposite. Otherwise, negative exponents can be kind of confusing. So I end up with 1/2 cubed. The answer to this is not -8. You can't go in the hole by dividing. Okay, it's 1/2 cubed, which is 1/8. And I apologize if you don't hear me too good today. I'm fighting something really bad in my throat, and so I apologize for that. Now the next one, I got a fraction to a negative power. The rule on that is to take the reciprocal fraction and change the power to its opposite. So it's going to be 5/4 to the power 2, and then both the numerator and the denominator have to get that exponent. So 5 squared would be 25, 4 squared would be 16, and there we go, 25/16. Again, negative exponents have to be changed to positive exponents. So with a fraction, reciprocal the base and make the power its opposite. All right, so we've had positive power, we've had negative power, we've had 0 power, and now we have fractional exponents. Now fractional exponents, kind of what I call partial powers, and in fact, on a fractional power, what you need to remember is the numerator represents a power, but the denominator actually represents a root. 16 to the 1/2 is actually the square root of 16. You can prove that in a calculator. The answer there is 4. All right? So if I go to the next one, 8 to the 1/3, the power would be 1, the root is 3. So again, we can rewrite this. This would be a cubic root of 8, which is 2. All right? So if you run into expressions where you have a base to a fractional exponent, what I tell kids is you have to identify the power and the root, and then you got to ask yourself, what would it make sense to do first? Should I power it up and then root down? Should I root down and then power that up? If you're going to do these at all mentally, you're going to want to do the root part first. So when I got 8, I would be looking at the cubic root of 8 and then squaring that back up. So the cubic root of 8 is 2. 2 squared would make the final answer of 4. Okay? So these are called rational exponents or fractional exponents. Again, the denominator is the root and the power is in the numerator. So we want to look at that and say, you know what, 16 to the 3/4 is the 4th root of 16 cubed back up. 4th root of 16 is 2. 2 cubed is 8. All these problems can be done on a calculator, and you can check it on a calculator. But a lot of these you can do mentally. Here I've got 9 to the 3/2. Now this one, the power is bigger than the root, so we're ultimately going to get bigger than 9. But if we write this down, I have the square root of 9, the square root, and I'm going to cube that up. So the square root of 9, I hope you're thinking, is 3. I'm going to take 3 and I'm going to cube back up, and I would get 27. All right, I just covered everything you can do with an exponent that you could possibly see. Positive, negative, fractional, changing the way the bases look, and whatnot. This is the final deal then would be if you had a fractional base to a negative fractional exponent. Okay? So you got to draw on everything we've learned here so far, or looked at. A fraction to a negative power, anytime you have a negative exponent, it is the same as the reciprocal base to the opposite power, which makes it positive. So the first thing we need to do is flip this base to 16/9, and the power turns to its opposite. Okay? Now we want to remember, okay, what is this 1/2 power? It's a fraction. The denominator is the root, the numerator is the power. So this is truly just the square root of 16/9, which if you break that up, it's root 16 over root 9. They're both square rootable numbers, or perfect square numbers, so that would be 4/3. Okay? All right, let's try one last one here. 8/27 to the negative 2/3. Again, I always say flip it and fry it. I like to fish. Everybody who's had me in class knows that, and I like to eat fish. So you cook one side, you flip it, you fry the other side, and it's all good when you're done. You don't want one side raw. So here it is. It's a fractional base to a negative power. I got to flip it. So 27/8. Change the power to its opposite, and now I got a chance. Power or root first? We want to do the root. So cubic root of 27/8. And then that is going to end up being squared up. So it's kind of a piece-by-piece effort here. These are both perfect cubic numbers. They're cube rootable. So that would be 3/2. And you square that back up, and I believe we'll get 9/4. Okay? So, a lot of different examples with powers and a little bit of rootage here.